Example 3.5. In this example, we have a conical section made out of pyroceramic. The cross-sectional diameter is given as a function of x. We have the length of the conical section. We have the temperatures at each one of the ends, and we need to find out the temperature distribution T of x in a symbolic form. We also need to sketch the temperature distribution and calculate the heat rate Qx. We assume this problem to be steady, one-dimensional, it has no heat generation, and it has constant properties. We are going to start the analysis with the definition of Fourier's law and the rate of heat transfer. Qx is equal to negative K A dt dx. In this problem, area is variable, and we're going to define it as, since it's a circle, we say that is pi over 4 d squared. D is a function of x, so we're going to replace it as d over 4 a x squared. Therefore, this term becomes pi over 4 a squared x squared. We substitute now the variable area into this equation. So a q of x then becomes negative k pi over 4 a squared x squared dt dx. This provides a relationship of the rate of heat exchange as a function of x squared. The next step is to be able to get the temperature distribution as a function of x. Therefore, we will be solving this derivative, dt dx. The method that we will be using is separation of variables. The way that we're going to do, we're going to keep all the terms that are a function of x to the left side of the equal sign, all the terms that are function of t or temperature to the right of the equal sign. Therefore, we write q of x 1 over x squared dx, and we keep the constants on the right side, and we say pi over 4 a squared dt. Once we have separated the variables, then we're going to integrate. We're going to integrate from x1 to position x2, and the other side we're going to integrate T1 to T2. Notice that temperature 1 corresponds at the position of x1, and the temperature T2 corresponds to the position at x2. The integral to the left, we notice that the value of Qx is a constant, therefore we could take it out of the integral. The integral of 1 over x squared becomes x to the negative 1, and we evaluate this integral from x1 to x2. The integral to the right side of the equal sign, we notice that k, pi, 4, and a squared are constant, therefore we could take it out of the integral. So we could write, and the integral of dt is simply t, and we evaluate it from t1 to t2. If we substitute these four values, we get the following expression: kx is equal to 1 over x2, 1 over x1 is equal to k pi over 4 a squared t2 minus t1. If we solve this expression for kx, we find that kx is equal to k pi over 4 a squared t2 minus t1 divided by 1 over x2 minus 1 over x1. And this is the expression for q of x. Please make sure that you follow the procedure, do the derivative, and obtain this result. Since we already have an expression for the rate of heat transfer kx as a function of T2 and T1, we can now solve for T as a function of x. What we're going to do is we're basically going to follow the same process. We're going to integrate. The difference is now the limits are going to be x1 to x and T1 to T, so that we could obtain a function of T as a function of x. So we follow the procedure and we set that qx 1 over x minus 1 over x1 is equal to pi over 4 a squared k t minus t1. And if we solve this function for t, we say that t is equal t1 plus t2 minus t1, 1 over x2 minus 1 over x1 times 1 over x minus 1 over x1. Notice that this expression is obtained after we substitute the value of qx into this equation and we solve for t. This is the final expression for t as a function of x. Please make sure that you follow the process and able to create the same function. The last step is to create a graph of t as a function of x. Notice that the coordinate system are given to match the problem. From this problem, the 2 points that we know is that at x is equal to 2, the temperature is equal to T2. So we plot that point. And then at x is equal to 1, the temperature is equal to T1. From the function, we see that t is inversely proportional to x, and that looks to a curve similar to this. Please go over the details of the problem. Make sure that you're able to separate the variables, integrate properly, and get the expression for qx and t as a function of x.